Welcome to my channel. In the design and analysis of algorithm, today we are going to learn about backtracking method. So under this backtracking method, we are going to learn three problems: n-coins problem, Hamiltonian circuit problem, and subset sum problem. Backtracking is a search technique which is used for solving variety of complex problem by recursively exploring on different combinations of the choices to find the solution. It is mainly useful for solving, searching, optimization, planning and gaming problems. The main idea is to construct the solution one component at a time, and it will find the solution for the next possible choice. Likewise, it is moving. There is no option for finding the solution, means we can backtrack and find the alternative solution. So for this we are to construct the state space tree. So here the root node is considered as the initial node, and the first level it is used to represent the choices for the first component, and the second level is used for representing the choices for the second component likewise. So in the state space tree, a particular node is considered as a promising node if it leads to the solution. If the node does not lead to the solution, means we can tell it is a non-promising node. So in this state space tree, the leaf nodes are used to represent either the solution or it may be the non-promising node. So the non-promising node can be considered as a dead end. And usually we are performing the depth first search method. So until we reach the dead end, we are exploring on the state space tree. And if there is no more choice, we can backtrack and moving on to the next possible solution. So that if a particular node is dead end, means we can backtrack to its parent, and that location is also not leads to solution, means we can backtrack one more level up. So finally we are reaching the complete solution for the given problem. And this is the example for n-coins problem. There are n cross n chessboard is available. We have to keep n coins on the chessboard without attacking each other either horizontally or vertically or diagonally. So this is one example of 4 coins problem. There are 4 coins, Q1, Q2, Q3 and Q4 is there, and this is the 4 cross 4 chessboard. We have to keep all the 4 coins on the chessboard without attacking each other. So this is one of the solution for the 4 coins problem. Let us see about 8 coins problem. For this we need to use 8 cross 8 chessboard, and there are 8 coins available. We have to keep all the 8 coins on the chessboard without violating the constraint. There are 92 possible solutions available for the 8 coins problem. So this is the 8 cross 8 chessboard. Here we have to keep all the 8 coins on this chessboard without attacking each other either horizontally or diagonally or vertically. And this is one of the solution for the 8 coins problem. Let us see the state space tree for the 4 coins problem. Here we are constructing the root node without keeping any coins on the chessboard. So that is the empty chessboard. Now we are going for the first level for the first component, that is the Q1. So we are keeping the first coin in the first location of this chessboard, so that while I am trying to keep the second coin, there is no possibility for the first column. Likewise, if I am keeping it here, it will diagonally attacking each other, so that there is no possibility for the second column also. So for keeping the second coin, I have to keep it in the third column. Okay. So now I have to keep the third coin on the chessboard, but there is no possibility for the third coin. So this is the dead end. So I am going for the next alternative. I am keeping the second coin in the fourth column. So if I am keeping it here, I can able to keep the third coin here. So now I am keeping the third coin in this location, but there is no possibility for keeping the fourth coin. All the 4 possibility is not available. So this is the dead end. So now I have to keep track on here, that is backtracking, and find the alternative choice for the first coin. So I am keeping the first coin in the second column. So now I am proceeding. So for keeping the second coin, I am choosing this location. So I can able to keep the third coin here. So now I am trying to keep the fourth coin also. So now this is the solution for the 4 coin problem. This is one of the solution for the 4 coin problem. So in this way we have to find the solution for the n queens problem. So the thing is, we have to start from the root node and keep queen on any one of the location and explore that state space tree by keeping the second queen, third queen likewise. That is, each and every level we are using it for the single component, and if we reach the dead end, means we have to perform backtracking and move on to the alternative choice for finding the solution for the given problem. Next we can see about Hamiltonian circuit problem. A Hamiltonian cycle or circuit in a graph can be denoted as, it is a cycle that visits every vertex of the graph exactly once and it will reach to the starting node. That is, we are starting from the initial node, we have to visit all the nodes in the graph, again we have to reach the starting node. So if the graph contains this Hamiltonian cycle, means we can tell that graph is the Hamiltonian graph. So it is actually a NP complete problem because there is no efficient algorithms are available for this type of problem. But this Hamiltonian circuit problem can be used in our real-time applications like transportation optimization, network design, circuit design, robotics, game theory, traveling salesman problem, etc. Let us see one example for the Hamiltonian circuit problem. So this is a given graph. We have to start from the node A and we have to visit all the other nodes exactly once and we have to reach node A again. So this is the state space tree for the given graph. So we are starting from the node 0, that is the first node A, and there are 3 neighbors available. So now we are moving on to B here. Then from this B we are moving on to the next neighbor C, then from C to D, D to E, then E to F. So now there is no more option for reaching A, so that we can consider this is the dead end. So that we are backtracking and moving on to the next alternative for C. So now we are starting from E to D, again we are reaching the dead end. There is no possibility to reach A now. So we are moving next alternative for E, that is F. So now this is also dead end. So we reach the dead end. So now we have to move on to the other possibility for this B, because all these choices are reached to dead end. So all these are non-promising nodes, so that we have to backtrack one more level up and we have to find the alternative solution for this B. So now I am traversing from B to F. So F to E, E to C, then C to D, then D to A. So now I reach the solution. So in this way we can find the solution for the Hamiltonian circuit problem. So we can start from the root node and we have to find the alternative choices if we are reaching the dead end, otherwise we are reaching the complete solution. So this is the promising node, so that which leads to the solution. The third problem is subset sum problem. Here a set of positive integers are given and one positive integer D is available. We have to find the subset from this given set and the sum of the subset should equal to this D. So example, if you are using S is equal to 1, 2, 5, 6, 8 and these are the 2 possible subset, the total of this subset reach this D. So that for solving the subset sum problem, we can sort the elements of the set in increasing order so that we can take like this: S1 less than or equal to S2 less than or equal to Sn. So let us see the state space tree for this example. S is equal to 3, 5, 6, 7 and D is equal to 15. So the root node which is used to represent the starting node, and we are constructing this state space tree as the binary tree, so that the left child and right child can be constructed by inclusion and exclusion of the set value. Let us see one example for the subset sum problem. The given set S contains 3, 5, 6 and 7. It is in increasing order and D is equal to 15. And this is the complete state space tree for the given problem. Here we are starting with the node 0 and it is a binary tree. So the left child is inclusion of the set value and the right child is exclusion of the set value. So first element is 3. So with the 3 and without 3. So now I am adding 3 here. So I have to take the second element 5. So with 5 and without 5. So I get the value 8. Now I have to take the third value 6. So with the 6, without 6, so with 6 I can get the value 14, and without 6 I can get the value 8 again. So now I am trying to include the fourth value 7. So if I am adding 7 with this 14, it will greater than the value of D, so that it is a non-promising node, does not lead to the solution. So we can consider this is the dead end. So we can move on to the next choice, without 6, and here from this node I have to include that fourth node 7. So with 7, then without 7, if I am including 7 with this node, I can get the value 15, which is equal to this D. So this node is the solution. Now if I am taking here, if it is less than this D, so that we can take it as the non-promising node. Likewise, I can move on to the other possibility also. So in some example, there may be more than one subset is available, so that we have to go on to all the possible paths, and here all these nodes are considered as the dead end because it does not lead to the solution. So in this example, here only one solution is available. So now we have to take the subset from the root node. So we have to take the path like this: first with 3, then with 5, then without 6, then with 7. So after reaching from the root node to this leaf node, I can get the solution for the given problem. So I can get one subset. So in this way we can construct the state space tree. So for all the example, we have to start with this initial node, and we have to construct the binary tree by the left side is inclusion of the set value and right side is exclusion of the set value. For each and every leaf node, we have to find the solution if it reach the value of D. If does not reach the value of D, means we can consider that particular leaf node as the non-promising node, and we can consider it as a terminating node. So in this way we can find the solution for the subset sum problem. I hope in this video you got some idea about backtracking method with the examples N-Queen's problem, Hamiltonian circuit problem, and subset sum problem. Thank you for watching.